Question 31. Show that the functions y is equal to cx square plus x plus 3 is a solution, though not unique, of the initial value problem x square y double dash minus 2xy dash plus 2y equal to 6 with y of 0 is equal to 3 and y dash 0 is equal to 1 on minus infinity to infinity. So we have a function here and we need to show that this is a solution of this initial value problem, this differential equation and this initial values. And we have to show that it's not a unique solution. Okay, so let's see whether this given function is a solution to this differential equation. For that we will just note given x square y double dash minus 2x dash equal to 6. This is given one. This is our given function. Now we can differentiate dx with respect to x. 1 2 y dash equal to 2cx plus 1 and C 4. Now let's apply these values into 1. LHS becomes x square x square into 2c minus 2x into 2cx plus 1 plus 2 into y. Y is cx square plus x plus 3. So we get 2cx square minus 2cx square sorry. This plus this 4cx square minus 4 square minus 2x plus 2x that's equal to 6. So our equation is a solution to this differential equation. Now let's see whether it satisfies the initial values. We are given y of 0. Y of 0 is equal to, our equation is cx square plus x plus 3. So c into x square is 0 plus 2x 2 into 0 plus 3 is equal to 3. So y of 0 is equal to 3. That is the given value. Y of 0 is equal to 3. It satisfies. Now let's see y dash 0. Y dash 0 equal to y dash, we got y dash as 2cx plus 1. So 2c into x is 0 plus 1 is equal to 1. So y dash 0 is equal to 1. So that is also satisfying. And comparing, so that satisfies. So now if we compare our this function to a general form, the general form is given by a0x a0x into y dash plus a1x into y dash, y double dash, a1x into y dash plus a2x into y equal to r of x. So we are just going to see whether uniqueness theorem applies here. So to see, so we can just we wrote down a second order linear differential equation, general equation, and comparing the coefficients of the given differential equation, we can see that a0 is x square and a1x is minus 2x, and a2 is 2 and r of x is 6. So we are comparing this form with that, therefore we get comparing. So let me write, give this v4, this is 5. So comparing 1 and 5, we get a0x equal to a0x is x square. I will, instead of scrolling it again and again, I will just copy this part down so that you will understand. Sorry. So we can now easily compare a0. So comparing a0 x equal to x square, a1x equal to minus 2x, a2x equal to 2, and r of x equal to 6. Now we got these constants. These are continuous functions which is defined on minus infinity to infinity. But we can see that a0x is equal a0 of, when we plug x value as 0, a0 of 0 equal to 0, and 0 is an element in minus infinity to infinity. So the condition for uniqueness theorem fails here. For uniqueness theorem, a0 x0 should not be equal to 0, where for any x0 element of the interval defined. So we cannot apply uniqueness theorem and claim the solution is unique. For the simplicity, I will just go through the existence and uniqueness theorem once. The existence and uniqueness theorem states for a second order linear differential equation of this form, a0x into y double dash plus a1x y dash plus a2x into y equal to r of x, where a0x, a1x and a2x are continuous functions on an interval a to b, and a0x is not equal to 0 for each x element of ab. So this is the condition that failed in our example. Then there exists a unique solution yx of 1 satisfying y of x0 equal to c1, y dash x0 is equal to c2. Defined over this interval. So this is what uniqueness, existence and uniqueness theorem states. So what like we saw, our a0x was x square, which was defined over infinity to minus infinity to infinity, and we can see a0x goes to 0 at x is equal to 0, x0 is equal to 0. If we take x0 as 0, it goes to 0. So this fails. So in our case, the uniqueness theorem fails, and we can see that from the steps we can see that this y irrespective of value of c, y of 0 goes to 3 and y dash 0 goes to 1 at x0 is equal to 0. And x0 is equal to 0 is a point in the defined interval. So we so if we take for this it is a solution for different real values of c, as it satisfies the differential equation also. All the terms with c cancels out. So here also it satisfies the differential equation. And if we take two random examples, say y equal to 2x square, giving c's value as 2 plus x plus 3, and say y equal to 3x square plus x plus 3. These two functions, these two are two functions. These two functions satisfies the differential equation and the initial value, since irrespective of c at x is equal to, if we take x0 is equal to in both these cases, y of x, this y of x satisfies the differential equation, and y of 0 is equal to 1, and y of 0 is equal to 3, 3 and y dash 0 equal to 1. So it satisfies these conditions. So these two are two solutions for the differential equation, and we can clearly see the solutions are not unique in that sense. So this is the solution. So we have shown we cannot apply uniqueness theorem, and there are more than one solutions to this differential equation, and this answers the question 31.